Hi guys, I hope all of us are doing great. I'd like to welcome each and every one of us to my channel of Honesty Sciences and Mathematics TV channel. And also request members who have not to subscribe to kindly go to YouTube, search Sciences and Honesty Sciences and Mathematics TV channel. Subscribe and engage us on the comment section for more. Now in this specific discussion, we're going to consider two phases of the same substance in equilibrium. And of course, we're going to see that we're going to consider the case of temperature and pressure. And see that if we try to supply temperature to this, or the heat energy to these specific phases in equilibrium, there's going to be, of course, what we refer to as the concept of equilibrium being maintained. And this means that we can be able to give the Gibbs free energy from our last discussion in form of equation. We had said that the delta is going to be given under constant temperature, and pressure is going to be given as, of course, we have given at smaller than or equivalent to 0. And we had attached two conditions for this using this specific equality sign, whereby we say that if delta T Tp is going to be given as 0, and therefore this is going to imply the concept of equilibrium. So therefore, we're going to consider two phases which are going to be given in under constant temperature and pressure as such, and try to see what are some of the effects of increasing or withdrawing heat slowly from the system. And the concept of increasing or withdrawing heat from the system, and how this particular case of equilibrium is going to be maintained. So therefore, for this specific case to be achieved, the equal amount of some substances is going to be therefore considered, and of course they are going to be having the same free energy whenever they are going to be in equilibrium. And this of course is going to be the case for, if we consider the phase for A or B, we can be able to represent the Gibbs free energy of these two specific phases as Ga, and this is going to represent the Gibbs free energy for phase A of this specific substance, and Gb for the second representation of the two phases in equilibrium respectively. Now, a change in temperature is going to, of course, result in an appreciable, or rather a significant or a corresponding amount of pressure being changed. And of course, this is going to ensure that the concept of equilibrium is maintained. Therefore, we can be able to represent the change in temperature or pressure in this specific case, so that the aspect of equilibrium is maintained as I've mentioned. So I'm going to consider two cases whereby a change in temperature from T with this particular amount of Td is going to correspond to a change in pressure, as I've said, of a corresponding amount of P plus D, P given as such. So therefore, if we were representing the Gibbs free energy for the two states of or the two phases of A and B, we can as well, of course, have this specific idea being taken to the change in free energy of the system for phase A and B, whereby we're going to have the change in free energy for the phase A given as Ga dGa, and then the change in free energy for phase B given as Gb plus Gd. So this is going to be dGb for the two phases respectively. So therefore, an increase in the temperature is going to have a corresponding increase in pressure in the two phases, of course, of this specific substance. And of course, an increase in Gibbs free energy for the first phase is going to have a corresponding increase of a Gibbs free energy over this second state. So this is going to ensure that the equilibrium is maintained. So for us to ensure that equilibrium is maintained, and then therefore the Ga is going to be equivalent, or the Ga is equivalent to Gn. So that is at the state of equilibrium, the two are going to be the same. So we can take the elements on the right side and do an equation whereby we're going to see that this particular change of a dA is going to be also implying the change of a dB of this second phase in equilibrium. Now we had talked about the representation of Gibbs free energy in our last equation, whereby we had given the dGa, just the dG in general being given as V dP minus S dt given as such, whereby an element of S is going to imply, of course, entropy, and V is going to imply volume. And this is going to be the change in pressure and change in temperature, as we said, from this specific case, as we are going to consider. Therefore, the two representations for dG and dGp can be represented using these particular equations, whereby we're going to have this particular dGa representing the change in volume of A, and then the change in entropy of A being given as such. And of course, the second phase for B, it's going to be given as Vp and dP minus SB dt respectively. So these are going to be the change in Gibbs free energy of the two states of or the two phases of that particular system, and that of course is going to assist us come up with the ratio between this specific aspect of dP and dt, as I've said. And of course, this is going to give us the relationship between entropy and volume, or the ratio between entropy and volume given as such. So we can be able to achieve that by trying to have of course, an equation that is going to represent the two, whereby I hope this one is clear. So we are going to have a relationship that is going to represent the two variables, or the two phases, whereby the VA dP minus SA dt is equivalent to VB dP minus SB dt at equilibrium. So generally, then therefore, this is going to give us a ratio of dP over dt being given as SA, or rather SB minus SA all over VA VB minus VA. So this is just an evaluation of this specific equation, and then we're going to have this one giving us a ratio between change in S over change in V given as that. So this is going to be the implication of a change in entropy for SB minus SA and VB minus VA, which are going to be given in that specific order. So the change in entropy in this particular case is going to be accompanying various the phase changes for A and B. And of course, we're going to see that this is going to be considered in the case whereby if the temperature is raised, we can be able to have a particular version of this specific aspect of entropy, whereby we have said that entropy can be given as a ratio between Q over T. And of course, in this particular case, we have considered this Q as the heat absorbed. Therefore, this is going to represent the change in enthalpy over T. And from the various phases that we had seen that under constant condition of temperature, we can be able to explain the heat of vaporization, the heat of fusion, which are going to be involved in this specific phase changes. Therefore, from this, we can be able to give a version of this specific representation, whereby we're going to have the dP over dt being represented as, so this is going to be the dP over dt being represented as change in enthalpy all over the temperature VB minus VA given as such. So this is going to be the case whereby we're going to consider the heat that is involved at delta H as the enthalpy absorbed per mole in the particular phase. And this is going to have an implication over this specific representation that we're going to have in our final case for this. So this is going to be referred to as the Clapeyron Clausius equation, and it's going to assist us try to, of course, describe the phase changes in equilibrium of these two specific phases for A and B. So we're going to apply the various aspects of this specific equation that we have discussed, and of course, perhaps in application areas whereby we're going to do it in forms of a problem set, it's going to be complementing on this specific video. So catch us in our other videos whereby we're going to talk about the concept of free energy and equilibria, and this is going to be shedding more light for us in trying to understand the various aspects of the different variables that we have used for temperature, enthalpy, entropy, and the, of course, the Gibbs free energies and the moles free energy that we have measured in our previous video. So that is it for now. Catch us in our next video and check our description boxes for various links of other videos which are related to this. So that is it for now. By God bless you. Catch us in our next video.